We are now ready to look at an example of charges in a three-dimensional arrangement and using Coulomb's law to find the forces between those charges. Our example is based on this design of the charges at the points of a pyramid, and you notice that the arrangement of the charges, you have two positive charges and two negative charges. With this example, I'm going to go through the process to find the force on charge Q4. The other charges, forces on the other charges are in the examples in the notes, and you can look at that at another time. But once you understand how to do it for the first charge, for one of the charges, the other charges are fairly simple. Now, the coordinates are in a tuple. You notice this three-number arrangement here. So you have the I coordinate, the J coordinate, and the K coordinate. And so let's look at directions of forces, just to kind of get an idea of what we're looking at. Well, with this charge Q1, you can see there's going to be a force due to charge Q2, and they're going to be attractive. So you're going to have one force going in this general direction here. And for Q3, it's going to be opposed, so it's going to want to go the opposite direction. And for Q4, it's going to go in this elevated direction. So there's all the charges that I have for Q1. For Q2, I'm going to have attractive force towards Q1, an attractive force towards Q3, and a repelling force. It's going to be kind of downwards at an angle for Q4. Q3, it's going to be repelled from Q1. It's going to be attracted to Q2, and it's going to be attracted to Q4. Q4 is going to have an attraction with Q1, Q3, and a repulsion due to Q2. So we can keep track of these. The formulas will keep track of this for us in these directions. We don't have to worry about angles. There's really no way of doing angles in three dimensions. You'd have to maintain two angles, and it's just not worth it. You'll get confused, you'll get messed up. So 3 dimensions, you got to work in the Cartesian coordinate plane and the coordinate system to do these. So let's write down what we're given here. We have Q1 is equal to 10 millicoulombs, and the coordinates are 3, 0, 0, and the units are in centimeters. Q2 is equal to minus 30 millicoulombs, and its coordinates are 0, 3, 0. Q3 is 15 millicoulombs. Coordinates are negative 3, 0, 0. And Q4 is minus 5 millicoulombs. And its coordinate is 0, 1.5, 3. So now we have all of the information. Now we can start to calculate some of the values. Now remember that our formula for the force is equal to K of the charge, Q1, Q2, over the distance R21 squared times R hat 21, or we can write this as K of the charge, Q1, Q2 over R21 to the third times R21. So we can use either of these formulas to come up with the values that we need. I'm going to go and show how to use the unit vector just so that it's clear. You can try to use the formula later if you want and verify that it actually is true. So for our formula for charge 4, I guess we can let's use charge 4-1 just as an example. Probably be better to do this. This is going to be 1-4, and this is going to be 1-4. Okay. Well, I'm going to have to find all of my distances. So I'm going to need to find R14, R24, and R34. Now remember that to find the vector, it's going to be R4, hate it when it writes a 9 there, minus R1, and that's going to be equal to R4 is 0, 1.5, 3 centimeters minus 3, 0, 0 centimeters. And that gives me, well, 0 minus 3 is minus 3. 1.5 minus 0 is 1.5. And 3 minus 0 is 3 centimeters. This is going to be R4 minus R2. And we have R2 is 0, 3, 0. And that leaves me with R24 as 0 minus 0 is 0. 1.5 minus 3 is minus 1.5. And 3 minus 0 is 3 centimeters. And now I have R4 minus R3 for the last R3, 4. And R3 is minus 3, 0, 0. So I have 0 minus a minus 3 is 3. 1.5 minus 0 is 1.5, and 3 minus 0 is 3. So that is the distances. Now I can come up with my vector, my unit vectors. And that's going to be R1, 4 over the distance. And the distance is just going to be minus 3 squared plus 1.5 squared plus 3 squared. And I forgot to put in my units because it's very important. And the reason why it's important is because the unit vector should have no units, and if you notice, my units are going to cancel out because I'm going to have centimeters squared square root. That just gives me centimeters, and then centimeters there. And now my unit vector is going to be equal to, see, that's R1, 4. And I'm sorry, looking at my notes here, 1, 4, there it is. So it's going to be minus 0.667, 0.333, and 0.667. And that just takes into account that you're just dividing each of these components by this denominator. That's how we come up with the unit vector. Okay, so now we have R24, and we're going to have R24 divided by the distance, and we have 0, comma, negative 1.5, comma, 3 centimeters over square root 0 centimeters squared plus minus 1.5 centimeters squared plus 3 centimeters squared. Take the square root, and that leaves me with 0, comma, negative 4 point, oh, sorry, messed that up there. So negative 0.447, comma, 0.894. And last but not least, R34, and our vector 34 was 1.53 centimeters over square root of 3 centimeters squared plus 1.5 centimeters squared plus 3 centimeters squared. We have square root, and our unit vector is going to have the values 0.667, comma, 0.333, comma, 0.667. So those are our vectors and our unit vectors for charge 4. And now, in the next video, we're going to look at how you calculate the forces based on the Coulomb's law, the vector form.